Welcome back. I think you must have organized yesterday. You already found the fact that the person is very one-dimensional. Everything is on the massive scale. So this makes you focus on the lecture. So our today's first lecture will be Professor DeMarco's lecture on localization and related measurements. Welcome.
Okay, so as I mentioned yesterday, this last lecture I'll give, and I have to warn you, unfortunately I have to leave right afterwards, so I don't have time to stick around and chat, will be about what people have measured in ultracold atoms that looks like localization. And I'm going to take a kind of agnostic point of view, and I'm not going to make very strong statements about whether it's MBL or other things. I mean, the only places I'll point out what people think localization, what kind of localization is happening is when it's clearly Anderson localization, which is what I'll lead off with. So that's about that. So the other thing let me say about this lecture is I'm not going to go very deep into anything. I'm mostly just going to give you an overview of what's happened and what's been done and how people measure things in these experiments. How do people look for localization? What do they do in the experiment? What kinds of things do they measure? And then, there's lots of references, and then you all can go and dig deeper into what interests you most. All right, so there's kind of two ways to look at or categorize what's in this talk. The first way is about types of measurements. And so I'll talk about sort of 4 different types of measurements today. One is diffusion measurements, coherence measurements, excitation spectrum measurements, and transport or relaxation measurements. Okay, so and I view these as being very much connected. In fact, diffusion is very much related to transport and relaxation as well. So that's one way to look at it. And another way to look at it is the type of models people study, right? So I'll talk about Anderson localization in 1D and 3D. I'll talk about disordered Bose-Hubbard models or dirty boson models, disordered Fermi-Hubbard models, and then attempts to find many-body localization in different dimensions. Okay, so it's another way to look at it is sort of like what are the types of models people are making using ultracold atoms. So I've tried to take some unified point of view here and just sort of put this all together and have more organized the talk in this way, talking about the different sorts of things people have looked at. And like yesterday, please ask lots of questions, just stop me, and there should be plenty of time. Also, let me just mention, like the last talk, I've left a lot of people out of this talk, I've left a lot of techniques out of this talk, and so there's a lot more out there than what I'll mention today. Okay, so the first sort of topic I'll talk about is one which occurs chronologically. So it's sort of where people got started with ultracold atoms looking for localization, and that's looking for Anderson localization via diffusion measurements. All right, so that's the first topic I'll talk about. Okay, so the first experiments with disordered ultracold atoms were in 1D, where diffusion was measured. And I should warn you, so the earliest experiments were by Urbana's group and Guscio's group and Espé's group. Urbana stopped working on disorder very early on, so a lot of the early results are from Guscio and Espé. And I should just mention also that if you're reading through papers chronologically, just be careful because some of the earliest papers, people thought they saw Anderson localization, but they were seeing something kind of different, and so you have to read through several years of papers before the whole picture becomes clear. So there was some confusion in the earliest papers. I'm going to skip that confusion here and just jump, straight to the chase. Okay, so I'm going to show you information about what was done in Espé's and in Guscio's groups where they first saw Anderson localization in 1D and show you what that looked like. So this is Espé's measurement, and I showed you a little bit about this yesterday, where they use a focused laser beam to make a one-dimensional trap for atoms. So they had a one-dimensional sort of guide that the atoms could expand along, and they had a trap. So this experiment, which was really Philippe-Poyet's experiment, was published in 2008. They used a rubidium-87 BEC, and so they start actually with a BEC in this trap with the speckle present. And then what they did is they shut that trap off. So they had a trap, they shut the trap off, and they let the atoms expand along this tube through the disordered potential. And this BC, this atom, there's not a Feshbach resonance, they're bosons, there's not a Feshbach resonance you can use to turn the interaction off. So these were quite interacting. And the initial expansion here was driven by that interaction energy until the density was so low that the interactions became negligible as a fraction of any other energy scale. So the idea here is that they let this initial expansion drive the density down to the point where the system became essentially non-interacting. Okay, and then everything past that point should look like Anderson localization. And the disorder they use was speckle disorder, where the shape projected onto the system from like a vertical direction. Or in this plane, I can't remember. I think it this way. Okay, so that was one experiment. I'll show you what they observed in a minute here. But the other experiment I want to bring up is Inguccio's experiment. And that was an incommensurate lattice experiment, which I told you about yesterday. And again, they had BEC in that experiment with a trap. And it was a potassium-39 BEC. Now, potassium-39 is an atom which has a very accessible Feshbach resonance. So what they did before they did anything, look at any kind of expansion physics, is they set the scattering length to 0. So throughout the whole measurement, in contrast with the space measurement, the atoms are not interacting. Right? So this is really a non-interacting gas. And they use incommensurate lattices, so it's kind of quasi-disorder of this Aubrey and Drey model. And what they did was they shut that trap off, and then they let that gas expand through the disorder, the incommensurate lattices, and watch what happened. Okay, so those were the first measurements in 1D. So what should you imagine? I'll say a little bit about Anderson localization, building on top of what Vadim talked about yesterday, and I'll do it my hand-wavy experimentalist kind of way. So what should you expect happens, and what's a cartoon of Anderson localization as these particles propagate through here? Well, I at least think about Anderson localization as a limit of weak localization, and a way to think about what was happening, again, in the most hand-wavy undergraduate kind of way, in those experiments is the atoms are all a source of waves, right? So those waves expand through the disorder potential, and they scatter off the disorder, leading to new sources of waves, and those waves scatter and they propagate. And so it's this very complicated interference pattern which now forms from all these propagated different waves. And this picture, of course, only makes sense when the mean-free path for the scattering is much longer than the wavelength, which I've sort of drawn on that limit here. And we know what that does is that complicated interference, for reasons I think Vadim will explain in a much more sophisticated way, leads to a reduction of the diffusion constant. Okay, and let me just skip this picture. This is kind of what Vadim was starting to talk about yesterday in a much more lowbrow way. This is an argument due to Bergman, Langer, and Neal about why that happens, so let's just skip that. Okay, so when that scattering becomes strong enough, you get Anderson localization, where now that interference away from the center of the source of waves becomes complete, and you form these exponentially localized states. All right, and that's Anderson localization. And this is defined by the diffusion constant being 0. So what they're kind of looking for in these experiments is exactly that condition, this sort of diffusion constant go to 0, and they're looking for these exponentially localized states. Okay, one other thing I should mention is that there's this Gang of 4 paper. There's another crucial part of sort of thinking about what should happen here, and then other things I'm going to talk about. There's this Gang of 4 paper, a very famous paper, where they looked at what happens in Anderson localization in different dimensions. And what they found in certain limits is that for an infinitesimal disorder in 1 and 2 dimensions, all states are localized of any energy. And in 3D, only states with energy less than a mobility edge, where less than a single band system means something kind of funny. But in any case, there are only certain states defined by a mobility edge and energy that are localized. All right, so we should look for this kind of physics to happen here too, but there's a lot of caveats with these statements. This is really just for an infinite system and an infinite time, and there's also assumptions about the disorder built into this. And I'll show you how, for example, that one is violated in one of these experiments. Okay, so here's kind of what they measured, and I'll stop and see if I can get any questions out of you. Here's the SPAE experiment, here's the Inguccio experiment, so I'll sort of put these next to each other to show you what they observed in these 1D experiments. So let's see here. So on the top panel here, they're showing the density on a semi-log plot after they've waited quite a long time for the atoms to expand through this disorder. 0.8 of a second, 2 seconds. And one thing you can see is that out where the atoms have sampled the disorder and scattered off of it many times, they're developing these exponential tails. They're kind of a hallmark of Anderson localization. They also are able to fit these tails and find a localization length, which they plot here in millimeters, so it's quite long. It's, goes up to almost a millimeter, which is a huge length scale. Remember, I told you about the length scales and these experiments on the time scales. One thing I want you to keep in mind, certainly as you go and investigate papers on your own too, is that these measurements go over very, very long length and time scales compared to the natural time scales in these systems. One thing you can see here is one thing that's kind of fun in these experiments too is you can see the time dependence. So this is a plot of that localization length that's measured from that fit versus time. You can kind of dynamically watch the system localize and assume a sort of static profile. All right, and that's something which is, I would say, that dynamic property of localization, how localization occurs in time, is not something which has been explored that much really, but I think is an exciting question to look at more carefully. Okay, so then what's over here? So this is for some fixed amount of strong-ish disorder. These are pictures taken from Iguchio's experiment. So this axis is time, and what you're watching is the gas expanding for different times inside that disorder potential, and for different amounts of disorder. So here's no disorder, and here's strong disorder. This is very strong disorder. And you can see what happens is, naturally, when you let the atom gas go, is it expands out into that 1D tube. And it doesn't look very 1D here because they've turned off the whole trap and let it expand after some time. But then as more and more disorder is applied, there's some sort of continuous behavior here where eventually it looks like the system's not expanding at all. And so then what they did was they measured the width of this gas, so that's the width of the gas in this direction, the direction along which it expands, versus disorder, sorry, that's the axis here, here's 1, 10, 100, disorder divided by their tunneling energy. They can kind of see for sufficient disorder, this is measured out at 0.75 seconds, that width, you can see things look like they're becoming sort of static and localized. Okay, so those are the first measurements, diffusion measurements of localization of 1D. And this was pretty widely accepted as being Anderson localization. Any questions about this? Yeah?
Is there any reason you start with the BEC, or is that just a product of
yeah, it's an interesting question. I think they decided to use a BEC in this experiment, right? They could have not cooled below TC. I think they decided to use a BEC in this experiment. And this later became important because they start with a relatively narrow range of energies. And that makes the interpretation of the data easier in some ways. Yeah.
If you come the geometry of the system, you said this is an energy system, but it expands, so it becomes 3D.
No, it expands just along one direction, right? So they use this is the reason I told you some of these things. They use a focused laser beam that's red detuned. So it makes kind of a guide for the atoms. They expand just in one direction.
So it stays always there.
Yeah, that is always left on
Okay.
until they turn everything off to take an image.
Okay.
Yeah. Okay, so in some sense it's quasi 1D,
Yeah.
right? Which is another reason this sort of scaling argument does not necessarily completely hold,
Okay.
right? Because it's not really 1D.
Yeah.
Yeah. Right, and that was a caveat I forgot to put up there, is nothing's really 1D, nothing's really 2D. Things are really 3D. Okay. So let me tell you more things they found out, some more things that were, I can't remember why I put this up here, but, oh yeah. Iguchio also carefully went and tested how exponential those tails are. So, this is a little complicated, but they fit the profile to some function which could interpolate between a Gaussian, which is what you expect if you just let the gas expand without disorder, and something exponential. And that fit value here, which is shown versus disorder, is 2 if it's Gaussian, and then it's 1 if it's exponential. And so they carefully studied sort of the changeover to having exponential tails, and they found the tails are very exponential within their error bars. Okay, so then I want to show you from a space experiment with speckle something that's different here than you might naively expect. And in that experiment with speckle, there is actually kind of a mobility edge present that they were able to observe. So, I'm sorry, this doesn't show up that well in this projector, but here from a space measurement in a certain regime is measurements of the localization length versus the disorder strength. Okay, so you can see as they crank up the disorder, the system becomes more and more localized, the localization length shrink, and this is sort of simple lowbrow reason that happens. And actually, using the board approximation, they're able to do some theory here. It's a non-interacting system, you should be able to do it, and figure out how the localization length depends on various things, like the maximum allowed k-vector of the atoms and the spatial length scale of the disorder. And one thing that's funny in the system, this is funny for two reasons, is that if you think about it, let's say you have a lens you're using to make the speckle, and it's uniformly illuminated. Well, there's a maximum angle here that happens where the rays can come in from the edges of the lens and interfere. And that means in the Fourier spectrum of the disorder, that the spatial Fourier transform of the disorder, that there's actually a cutoff in spatial frequency. Because you can't have a feature that's smaller than what you get it from interfering two rays like this at this angle. And so what that does is that leads to a kind of effective mobility edge here where you see algebraic localization rather than exponential localization in certain regimes of the k-vector of the atoms compared to the spatial length scale, that cutoff in the Fourier spectrum. They were able to observe that exact thing, and the way they did this was that pre-expansion driven by the expansion energy of their gas, because there's a certain amount of interaction energy there, that leads to a maximum k-vector after that pre-expansion, because you just use up all that interaction energy. And so they were able to tune the amount of atoms that were present in order to tune that maximum k-vector and cross over between exponential and algebraic, which is not localization. Now, so this is kind of a funny thing that's present here. Is this reality of the properties of the disorder. But of course, this picture is not really right. This cutoff can't physically exist because, of course, the lens can never be uniformly illuminated. That's not allowed in nature. You're not allowed to have a sharp cutoff in that Fourier spectrum. So, we even need a more sophisticated theory here and understanding to completely capture what's happening. You can see their theory is not capturing the data particularly well either, based on this, this picture. All right, so there's still some questions there and things to figure out. And like I said, part of it is sort of the complexity of speckle and modeling it. There's plenty of work to do there still. Okay, so that was it for 1D Anderson localization. I was going to talk about 3D next. Yes? All right, so let me talk about measurements of 3D Anderson localization, which were also not very controversial in any way. Okay, so there's there's 3 measurements of 3D Anderson localization now. I'll talk about the first 2, which was from my group and from a Spade's group, or Fourier's group. They were in 2011, 2012. And in these measurements, what was done, let me just walk through what was done actually. So in my experiment, my group's experiment, of course I'm old enough now, I don't really do experiments anymore. I just go give talks like this. But we use this spin polarized Fermi gas, so these are really non-interacting particles. Okay, so it's kind of like in Gucci's experiment where they set the scattering length to 0. These are very non-interacting particles. In a Spade's experiment, they used rubidium-87. So ours is non-interacting, and here what they did in this experiment is slightly different than what they did in the past. They did 50 milliseconds of pre-expansion, so this interacting BEC could kind of blow itself apart through interaction energy, and then they suddenly turned on the disorder. Okay, where we slowly ramped on the disorder before we released the gas. Although we also looked at snapping on the disorder, it didn't seem to change anything. I should say something else here. So also we used a sort of thermal gas made up of these fermions. T over T fermi is about 1. So we had a very broad energy distribution, many different atomic wave vectors present. And let me say something else here, just to clarify this. In our experiment, we just had a single speckle beam, okay, that we let the atoms expand in. So we started them here, and it's diffusion measurement. So we had a trap, we turned the trap off, we let them expand through this single speckle beam. And a Spade's experiment, they had these cross speckle beams I told you about yesterday, where they took 2 speckle beams, one along this direction and one propagating along the orthogonal direction. And they made a cross speckle field where there's additional interference from the fact that you have these 2 laser beams with identical polarization crossing. And so the autocorrelation function is a little bit complicated, and it has these kind of stripes in it, in addition to sort of the speckle autocorrelation function. Okay? So this is what was observed by my group and the Spade's group. So in my group, the basic observation was we let the gas expand, and there were atoms that diffused away, but there were atoms that would stick around. Eventually we could see them stick around for a second in a narrow, localized looking feature. And in a Spade's experiment, they saw something very similar. So here are time sequences of data This is going out to, I'm going to have to go look. I don't know, screen here. Projector. So